have to use the inverse function?
Not necessarily. I mean, you're going to prove it for a specific map. You're going to go actually and solve it, and not in general. Oh yeah, for a specific map, you'll do it. So, okay. So why this is the case? Let's talk about the intuition, because, okay, it's a condition we're going to apply, but why it's really the case? Why this is a requirement for stabilizability? So let's talk about the intuition behind this construction, okay? Behind this condition. So the intuition behind it, and it's for the intuition, let's make it simple for. So this is a scalar now. Without loss of generality, I have my point to be the origin. Here is the origin, x naught is the origin. And I want to make it stable in some neighborhood. Okay? So if you want this to be stable, if you have a disturbance like this, x1, so x1 is positive. To make it stable and to bring it back, you need f of x1 and u of x1 to be what? You want it to be what? Negative, right? If I have a positive disturbance, I need to oppose it, so negative, and vice versa. If I have here x2 that is negative, I need to generate something that is positive. Okay? So, indeed, a necessary condition to stabilize this system, I need to have the ability to generate positive and negative speeds, obviously, right? Which means, I mean, if you generate some positive or some negative, it means that your map from x and u to here is onto. I mean, onto means what? I can reach all the possible values in the neighborhood. For one-dimensional, all the possible values in the neighborhood of the zero is just positive and negative values. Okay, so this is the intuition behind the thing. I'll draw another picture, that might be better.
But I have to do that like even smaller and smaller, right? Because, for example, f can have it can have a gap between the equilibrium and, let's say, some bound on the left side and some bound on the right hand side, such that
You
it's always.
need to do it smaller and smaller, which means that it's an onto in a small neighborhood. Onto.
Yes, if I can't make it smaller and smaller. I'm saying
you cannot.
Yeah, I'm saying if the magnitude of f.
Then it's not stabilizable. This is why the condition is we want it to be onto. So we want to generate all the things. So it's like this. Before going here, I will give you. Do you need this anymore? I will. Maybe I can write it where I can write it. I will erase this and write it here. So it's an alternative for the condition 3. So this is a paper by Orsi et al. 2003, relatively recent. He said, first of all, this condition actually is a necessary condition for the case of C node, just continuous feedback, not even smooth. Continuous system, continuous feedback. Obviously, you need this to be more than continuous for existence and uniqueness of solutions, but at least for the feedback, it allows continuous feedback. So Orsi said that the same condition, I mean the same set of conditions, but the first one, they are mandatory anyway. So the third condition is also a necessary condition for stabilizability using continuous feedback, and he wrote it in a different way. It's the exact same condition, but in a different way, and I like his way. He said that the image under F of any neighborhood of x naught and 0 in Rn Rm contains a neighborhood of 0 in Rn. So if this is x in Rn, this is u in Rm, and this is x dot in Rn again. This is your origin here, and this is, say, x naught and 0u. This is your map, right? F. Okay? So it says that we really need to generate all these points around the neighborhood here. Not from anywhere, from neighborhood here. So the image of any neighborhood here gives you a neighborhood there. If you shrink this guy will shrink too. Okay? The image, if you map any neighborhood around the origin here, the image should contain a neighborhood here, which means that you can generate positive and negative x dots. You get this one? It's exactly equivalent, but this is actually a bit clearer when you apply it to problems. We will see it in a minute. Any questions so far? If you have a question, stop me. I know it might be a little bit involved, but let's have an example.
The neighborhood on the line has to be open, right?
Yeah, any neighborhood here is open. Do you remember the system? Spent quite a bit of time with it.
Brockett integrated.
Yeah, the non-holonomic integrator. Some people call it the Heisenberg system, related to quantum. I don't know anything about that. So your f of x and u is u1, u2, x2 u1 minus x1 u2, and you want to see that this is an onto map. So how do you do it? How we do it? We equate this with some y's, y1, y2, and y3, and try to do what? Try to solve it for the y's, and so you solve for x and u in terms of what? It seems you can do it, because I have 3 equations, and I have how many free parameters? I have u1, u2, x1, and x2. I have 4 free parameters to satisfy 3 equations, so I have more freedom, right? It's not tight. It seems that I can do it, but let's see. The point is that you should be able to do it for any y's small enough. Okay? If making y smaller and smaller allow you to solve it, that's okay, because we require to arrive at neighborhood here. Any neighborhood, no matter how small it is. Okay? So make y small, whatever you like, epsilons. Try to solve this guy. So let's see, the y1 dictates u1, the y2 dictates u2, okay? Now these guys are dictated. Let's go to the third equation. I have some y3 here. In order to solve, I can solve for either x1 or x2. Solve for one and the rest, the other can be free. If you solve for x1, how you do it? It's y3 minus this guy divided by u2. So we're going to divide by u2. So it must be non-zero. But u2 is dictated by y2 and y2 is free. Actually, I can give you, here is a hard requirement, 0, 0, and epsilon. And make epsilon small, whatever you like. Right? This point is not in the image of f. So 0, 0, epsilon is not in the image of f, i.e. there is no x and u such that f of x and u gives you 0, 0, epsilon for any small epsilon, no matter how small it is. Okay? So it's not as trivial as you might think. Remember, this system was a small time locally controllable. We played a lot with it, right? The Brockett completes the triad, so it's a controllable system, but it's not stabilizable. And if you think about it, I don't have drift. I have just 3 states and 2 inputs. I should be able to do it, from an engineering intuition. It's just 2 two inputs and I have one extra state. And I don't have drift to resist. Nothing will resist me. Whatever you actuate the system, it will happen instantaneously. But this mathematics tells you that you can never stabilize it using feedback control law. That's interesting. Mahmoud, you have a question?
Yeah, so this has nothing to do with, let's say, if we find the Jacobian of the left-hand side, right?
No, because you have the Jacobian will not be invertible anyway. It's not square matrix.
Yeah, but if it has rank 3, for example, if the Jacobian has rank 3, this means that
around the origin. Yeah,
right.
you can try to do that. Yeah. Another example.
Professor, here 0, 0, epsilon is a counter example, right?
Yeah.
Okay.
So, try to solve it. That's okay. Try to solve it for the y's. You'll find yourself divide by u2 or u1. And for division, we as NG mathematician, we care about division. So you should ask yourself, are they zeros or not? And you immediately discover that they can be zeros. So this cannot be a solution. Another example that we also spend quite a bit of time with it, x dot, y dot, theta dot. Probably you know what I'm talking about. V cosine, V sine, and 0, 0, 1, the kinematic card, okay? So here is my map again. Here is my map. So this is cosine theta u1, sine theta u1, and u2. And I want to solve this for y1, y2, y3 for any y's, and if making them smaller will help you, that's okay. Obviously, the y2 is decoupled from the third, so the last equation can be satisfied without disturbing anything. It's okay. Let's focus on the first two. Now, if y1 is anything, if it's 0 in particular, this dictates either u1 is 0 or cosine theta is 0. Well, u1 can't be 0. Why? Because if it's 0, then it will dictate that the second is 0, and this may be any epsilon. Correct? So u1 can't be 0. Avoid that, please. So this gives you that the only viable solution is cosine theta is 0, right?
Which means sine 1.
Which the sine is 1, so you can use u1 to satisfy the second equation, fine, but cosine theta is 0 means theta is what? Theta is what?
Plus or minus
Pi over 2, some or its multiples. So it's not in a small neighborhood of the origin. Remember, here's the condition. I need that the image of any neighborhood of the origin, you need to give me. If I shrink this guy, if I shrink the required point here, I can get a point that is small enough. No matter how much you shrink epsilon here, the solution will always be pi over 2. So this point, we need this point to be in the image of any. Look at this. So this is why I like it. The image of any neighborhood. So any neighborhood here should give you a neighborhood there. Any neighborhood. So I give you a point in the neighborhood here that comes from theta's 90 degrees. Right? So again, this is. So the point 0, epsilon 1, and say epsilon 2 is not in the image of many neighborhoods, actually. Neighborhoods of 0, 0 in Rn across R. Any question about that? Any question, please? We're done. I like to, when I see an interesting condition like this, all of us, we should try to make connection with the things that are, we know it, we know it in the back of our mind, we know it by heart. What's the thing that we know by heart? That means the only thing actually in engineering, which is LTI. So the linear systems, we know it by heart. X dot equals AX plus BU. You're telling me that this condition is a necessary condition for stabilizability of this guy. Let's try to convince ourselves, at least for the linear systems, right? I know for linear systems that if the system is stable, it's stabilizable trivially, right? So how a stable system satisfies this guy? Stable system is stabilizable, so because this is a necessary condition, it must satisfy this condition, right? So how a stable system satisfies this guy? Can you solve this for y, for some given y? Can you give me the solution? A stable system, what do you know about the stable system? What do you know about the stable system?
So eigenvalue
The eigenvalues of A are what?
is negative.
Are negative, so there is no zero eigenvalue. So no matter how much you multiply them together, you will not get a zero. And the determinant of a matrix is the multiplication of the eigenvalues, right? So this guy is, there is no zero. If all the eigenvalues are in the left half plane, the determinant is not zero. If the determinant is not zero, then it's invertible. Then in particular, here is a pair of u and x that can do it for you. U is 0, x is A inverse y, because I can invert x, okay? So A inverse y and 0, okay? And we know more, we know if it's controllable, then it's stabilizable, right? The trivial thing in the linear system, again, it's simple argument. If this guy is unstable or maybe have a zero eigenvalue, I don't care because I can design, to make the closed loop thing and do the exact same thing. So one very last thing that I'll mention, actually, Kautsky, it's an interesting thing, just to have it in the back of our minds. 1989, he showed that for the two dimensions, just x and y in the plane, controllability implies stabilizability. And we're done with today's lecture. I'd like a few dependent, please can switch this because I'd like to discuss something about that.